Okay, so any problems with assignment, homework? You can ask me questions while I set it up. Yes. I can't really hear with this one. Yes.
What would you like to see ahead exactly? Like the zip with the
Yes, so all the files that I've uploaded, whatever files you have changed, give me in a zip folder.
You don't want like the executable file or anything?
No, all the code that you have written. You don't need to give me executables because I can run GCC and generate executables. You don't need to give me executables. Just give me the code. Whatever files you have changed, just um, compile them in a zip folder, upload. Right. So when is it due? It's due on the 15th, right? Saturday. And your homework is due on 18th? Okay. And you have exam on 18th. So that is fine. Oh. So are you having any specific problems related to the project? One thing I can say is that do not look at the test cases using Notepad. If you look at the test cases using Notepad, you'll get confused because it omits spaces, it omits line breaks. So look at the test cases using the VI editor or VIM, right? No, those two only in CentOS. Then you will see that the expected output makes sense. So that is one important thing. Any problems with the homework? Did anybody see the solutions to the homework? Does it make sense to you? The solutions?
Just to be sure, the plus sign, does it mean the same as bar or different?
Yes, no, it means the same as bar. The plus sign in your homework means the same as bar. Okay, no questions? Okay, so we can start our discussion. Oh, and by the way, I have, so with respect to office hours, I just said that you can do Tuesdays, Thursdays, right? 2 to 3. But what you can do is you can come any day from Monday to Thursday. Because I have 3:30 office hours from 2 to 3 as well. And most of the time it's empty on Mondays and Wednesdays. So 3:30, 3:40 does not matter. Just come 2 to 3 any day from Monday to Thursday, not Friday. Okay. Are the recitations helpful? Are they going well, or you have some problems with the recitation? Any specific requests? So everything is going fine. I have uploaded videos. I have uploaded 5 videos so far. I'm still uploading. So you can go check those 5 videos. So these 5 videos are up to 7. No, the 7th one I am uploading now. So you have until that point. Then I need to upload 10th. 10th we didn't record any video. 11th. I need to upload 11th and today's video. So you can check all those videos. So check those videos and make sure that they are good quality and you can hear me and all those things. You check those things. Oh, you can't see. So here. So all the class 2 to 5 are there. Just I need to upload 2 more videos. Any questions on the content that we discussed last class? Let's do a review. Quick review. So what we were discussing was semantics checking, and we said that semantics is kind of different from syntax. So programs, two different programs can have correct syntax, same syntax, same code even. But if we have different semantic definitions, the result might totally change. Right? So what do semantics tell us? Syntax tells us that okay, if you write the code in this way, then a machine can understand what you have written. Machine can read what you have written. But can it make sense out of what you have written? It can only make sense out of what it had written, what you have written, if it can have a semantics checker. So semantics checker basically allows you to make sense of programs. What does that mean? When you write C equals A plus B, what does it mean? Semantics checker lets you do that. So we were discussing semantics, and the first thing that we discussed was the most basic semantics of anything is declaration. Right? So we are starting to say, okay, how can we make sense out of declaration? And we saw that there are two parts to making sense out of declaration. If we consider a variable, there are two parts. First of all, the scope within which a declaration is valid, and second, how can we associate a name to a declaration? So that is name resolution. So there are two parts, scope and name resolution. First of all, if a variable is declared in certain space, can it be accessed in certain other space? That is scope. And then second, if we saw that multiple variables can have the same name. So variables with the same name can have multiple declarations. So when we are executing a code, if we want to make sense out of a code, one very important thing is which name goes to which declaration. So we saw some examples where the same name went to two different declarations, and based on how we associate a name to a declaration, our results change. So we talked about C scoping, we talked about dynamic scoping. Right? Static scoping, C uses static scoping, and we saw dynamic scoping, which C does not use, but we kind of forced C to use that dynamic scoping and see what was the result. Right? We saw some examples. Lisp uses dynamic scoping, and somebody said Scheme uses dynamic scoping as well. That I personally don't know. So we talked about declarations of variable. Then we talked about declarations of functions. How can we associate function name with a declaration? And we saw that in C it does not matter, because the function signature used by C is just the name of a function. But in C++ it does matter, because the function signature in C++ is not only the name but also the inputs. Right? In C, the signature is name. In C++, the signature is also name plus inputs. So in C++, we can have functions with the same name, but different inputs. So we can override functions. Right? So those kind of examples we saw, and based on which function definition we resolve, the results differ. Now we come to a very important topic, assignment semantics, and that is probably the most difficult part here. So assignment semantics means you make C equals A plus B, that is an assignment. How can we make sense out of this assignment? What happens when we write C equals A plus B? Okay. So what we need to do with respect to assignment semantics, we need to answer what are the exact semantics behind the following statement, x equals y. What do you mean by x equals y? Now this meaning of x equals y varies with different programming languages. So it depends upon programming language. We need to basically define four concepts related to an assignment. x equals y has four things, four different things. First of all, name. Name is what? Whatever variable you are using, x equals y, there has to be a name associated with that variable. Here, if you see x equals y, what are you doing? In some programming language, this might mean that you are updating the value of x somehow, right? In some other programming language, it might mean you are updating the value of y. But let's say in our programming language, we mean that we are updating the value of x by writing this code, x equals y. So that means we need to give a name to this declaration because x has to be updated. X is a name, right? So we have to give a name. The other thing that we have to do is to give a location. So why do we need to give a location? Now remember, we are updating a variable. We are updating a variable with a different value. That value has to be stored somewhere. If it's not stored, we lose it. So we have to associate a location with every assignment. What location, what value, the value of which location are you changing? So that is another important part of assignment semantics. So first part is which variable you are changing, that is the name. The second part is which location are you changing. The third part is binding. Now this is a different concept, we did not really talk about this. What is binding? Binding means you have a name, variable x, you have a location. What does this location correspond to? How is that name related to this location? There can be many different ways that a name can be related to a location. First of all, what does a location have? If you think of the CPU memory structure that we talked about maybe in the first class, right? Our basic CPU, which had registers, and in the registers it had the capability to store some values, right? And for each register we had address buses, right? A CPU can use a unique address, put it into an address bus and access a location. So there was an address and a value for that particular location. So x, that is the name, can be either associated with that address or can be associated with the value. So what is the association? That association is given by binding. So binding says whether x is an address or x is a location. No, whether x is an address or x is a value. What is it? That is what is given by binding. So that is another part of the assignment semantics. So name, which means which variable you are updating. Location, which means which memory location you are storing that update. And third is binding, which means how is that name related to that location. And finally, fourth is the value, the actual value that you are using to update the variable. So these four things are four different parts of assignment semantics. Now we need to have a way. To find a relationship between these four things, or at least to represent the relationship between these four things. So how do we do representation of the relationship? We use something called box and circle diagrams. Right? Box and circle diagrams. So what is it? The moment you have a declaration, right? The moment you have a declaration x, there is associated to x, there is a name, binding, location and value. How do you represent it? Name is x. You represent the location using a box. Just a box. So this corresponds to a memory address. Right? Then a binding corresponds to relationship between a name and a location. So if int x, you say x is a local variable or global variable, whatever, x has to be associated with the address. there has to be a particular memory address of x. If it's a local variable, it's the stack. If it's a global variable, it's in the RAM. There has to be some binding, some address associated with x, right? So that is the binding. And how do you represent the value? By a circle inside the box. So the moment you declare any variable in text, for each declaration you should have this box and circle diagram. If you have a char y, then same, you have y name, then a location which is represented by a box, then you have a binding, that character name to that location, you have a line that binds the name to a location, and inside you have a circle where you store the value. Right? So for every local variable, global variable, whatever you declare, you have to have a box and circle there. Now if you do x equals 5, what does this mean? Semantically, what does it mean? What is the assignment semantics here? X equals 5. What do you think it means? What does it mean?
Set the value of x to
Exactly. So what it means is that copy the value 5 to the location associated with the name x. Right? So you know that whenever we declare int x, we have that diagram. Any declaration, the first thing you need to do is take that name, have a box circle diagram like this. Any declaration. Now if you do x equals 5, then what it means that you take the value 5, copy it into where? Where do you write the value of 5?
Circle.
Inside the circle. So take the value of 5 and copy it into the circle. So that means that copy the value 5 to the location associated with the name x. This is the terminology we will use. Right? Copy the value to the location associated with x. So what does that mean? What does that mean by copying a value to the location associated with x? It means that this box is the location associated with x. Copy 5 inside the circle that is in this box. Right? Don't write the 5 here or don't write 5 here. Take the 5, put it into the circle. Right? That is what it means when we talk about copying the value 5 to the location associated with the name x. Right? So you take the value 5, put it into the circle. So when you do x equals 5, it means this. So that is our assignment semantics for x equals 5. That is the semantic. That is how we represent the semantics. Now if you have int y and make x equals y, what does it mean? Intuitively, what does it mean?
It's gonna bind them together.
Pardon?
It's gonna bind them
How?
by address.
Is it by address? These two are local variables. Mind you. So it becomes a little bit complex. So what does it actually mean? In English, what do we say? It says that copy the value in the location associated with y to the location associated with x. So by just looking at this definition, by reading it maybe 3-4 times, what do you understand? What you have to do is, for every declaration, you know there is a box and circle diagram. So for x there will be one, for y there will be one, right? Because you have two declarations. Now what do you do? Copy the value in the location associated with y to the location associated with x. What does it mean by that sentence? So copy the value in the location associated with y. Where is the value in the location associated with y?
Circle.
Inside this circle. Copy it to the location associated with x. Where is the location associated with x?
The other circle.
No, where is the location
Box.
associated? Yes, the location associated with x is this box. So it says that copy this value to this box, which means you can only write the value inside the circle. So you take this value, whatever was there in the circle of y, put it into the circle of x. So this is what it means when we say x equals y. That is the assignment semantics representation. Right. And let's see another example. What if we do x equals x? How will it look like? Can you think? How will it look like? The English definition is what? Just replace y by x. So copy the value of location associated with x to the location associated with x. Again, when we declare int x, we have to have a box and circle diagram. Now what happens? How does it look like? Yes. So she says that it will be a self circle, but self arrow. So you take the value of x and put it back in x. Might not mean anything, but this is how we represent. Right? Now, here what we have done is here we have just said very simple, just talked about very simple expressions. X equals y, x equals 5, x equals x, and so on. But we would like to have more complex expressions. X equals a plus b, or x equals a plus 5, those kind of operations. So in order to have that, we need to define certain things. How many of you know about L value and R value? Anybody knows about L value, R value? You know. Who else? 2 people. But everybody has written code in C, right? Everybody? At some point in your life? So in C, you have this concept of L value, R value. So what is it? Let's see. L value is an expression. So an expression is an L value if there is a location associated with the expression. Now this is weird. When will we have a location associated with the expression, and when we won't have a location associated with an expression? When do we not have locations associated with the expression?
It's normal.
Pardon?
It's normal.
I mean, that's the definition of R value. But can you give me an example? Yeah.
When we have like mathematical operation that
Yes, when we have mathematical expressions or just have numbers, right? Now, why doesn't it have a location associated with numbers or mathematical expressions? Why don't we have a location associated with that? What is the problem? What do we mean by location associated with the variable? First of all, what is meant by that?
You visualize it.
Yes, so what happens to the memory?
You get a story someplace in memory.
In the RAM, right? You're going to take an address, take a line of the RAM, take a register, and keep it for that particular variable in the RAM. It might be in the stack, it might be in the global data, does not matter. It might be in the heap, does not matter. It's a memory location in the RAM. Where do you store A plus B? Where do you store the result of A plus B? When you just computed A plus B and you do not know what is C, so you are trying to compute C equals A plus B, you are trying to execute that line of code, but you didn't really execute C equals that part. So you didn't store the value in C yet. You just computed A plus B. Where does that value reside?
Register.
In which register? In register R2. It is a CPU register. It is not in RAM. It does not have any address associated with it. It is just in a CPU register. So if it does not have any address associated with it, it will not have a location associated with it. Those type of values are called R values, where you don't have them in memory. You have in some register. You have them in some register. Right? So an L value is an expression if there is a location associated with that expression, R value is an expression is an R value if the expression has a value associated with the expression, no location. Right? Example, x equals 5. That 5 is in some register, and x, we have a location associated with x. Right? We know because we have declared x. So x is a L value and R is a, and 5 is an R value. So what does it mean? If you have this expression L value equals R value, it means that copy the value in R value to the location in L value. Right? Can we have this? 5 equals x? We cannot have. Why can't we have this 5 equals x? 5 isn't a CPU 5 is in a register, it's in a CPU register, but it is not in a memory address. Right? So what is 5? So what is that equal to operator? The assembly level equivalent of an equal to operator is you do move. Right? You do move from one place to another. Oh no, not really move, you do store actually, not move. So the store instruction requires the first argument to be a memory address. It cannot be a CPU register. Right? Store in, so this equal to sign does not correspond to move. It's not move. Equal to sign is store. Store requires a memory address where you want to store. It cannot be a CPU register. So that's why you cannot have 5 equal to x, which means you cannot have R value equals L value. This is not possible, having R value equals L value. It's not semantically valid, as well as you cannot really do it in assembly language, because store always needs a memory address as argument. It cannot take a register as argument. So that's why in code also you cannot have this as a semantically valid expression. So R value equals L value is not semantically valid. Can you have L value 1 equals L value 2? Yeah. X equals Y, right? So what does it mean semantically? It means that copy the value in location associated with L value 2 to location associated with L value 1. That's the example that we saw, x equals y. Right? Let's take some examples. A equals b plus c. Now here, do we have a location associated with A? We do. So A is an L value, right? Do we have a location associated with B? With B? We do. B is a variable. Right? B is a variable. The assumption is we have declared B in A, in B, in C. So we have declared all the variables. So B, we also have a location associated with B. Do we have a location associated with C? We do. So do we have a location associated with B plus C? No, we don't. Why don't we have location associated with B plus C? Because plus is an operator. And what is the function of that operator? It takes the value of B, loads it into R1, takes the value of C, loads it into R2, adds them up, loads it into R3. So that R3 is a CPU register, it's not a memory address. So B plus C is not an L value, it's an R value. But this is a valid semantics because A is an L value, B plus C is an R value. Is the value in the location associated with B plus value in the location associated with C. And that is stored in a register. It's not stored in some address, memory address. So B plus C becomes an R value. So what you do is you copy the value associated with B plus C to the location associated with A. That is the assignment semantics. So do you understand what is happening here? Why B plus C does not have a location associated with it? Because of the plus operator, it stores the results in the R3 register. And it's not an address. Now we go to a more complicated issue, pointers. Pointers are always complicated. Now, hopefully, after this discussion, pointers will be very easy. Will be very easy to do. Okay. So pointers have two things associated with them. The address operator, which is the ampersand, and the star operator, right? So we'll understand what are these two operators. So it is a unary operator, address, ampersand operator. It can only be applied to an L value, right? So you cannot apply it to an R value. The result is an R value. So the ampersand X does not have a location associated with it. It's just a value. It's in some register, the ampersand X. So what is it? The result is an R value of type T star. So if T was integer, then it will be integer pointer in T star, where T is the type of the operator. Now what is the value of that R value? The value is the address of the location associated with the L value to which ampersand was applied. Becoming a little bit confusing. So let's look at the box diagram. I really should be on this one. So the ampersand operator, right? So if you have an X, the moment you have declared int X, that means you have to have the box and circle diagram, right? Now what is ampersand X? So it says that this is an R value, right? Ampersand X is an R value. So it has to have just a value associated with it. Has no location associated with it. But what is ampersand? It is pointing to this box. This box has a memory address, right? 0x A F 1 2 3. (32 bit). Right. So this becomes 16 bit. No, 32 bit. Yes. So it has 0xAF12. This is the address of this box. So you take that address, consider that that is not an address, that is a value. Think of it like a value. So ampersand X becomes that value, which is actually an address. It is actually an address, but now if you use ampersand X becomes a value. So you can add to it, you can subtract from it, you can multiply it, right? Don't know whether it makes sense to multiply something to an address, but you can do that if you use ampersand X. So ampersand X considers that address to be just a value. That is the function of ampersand. Now we have another operator called the dereference operator star. That is also a unary operator. It can be applied to an L value or an R value of type T star. So that star can be applied to an L value as well as R value. Right? So what if I apply this? Star X. What happens to this? Pardon? Yes?
Point to the circle.
It will point to the circle. Because ampersand X is this address, so which means this address, and whatever value is in that address, so it means this. Right? So this star ampersand X points to the circle. let's take a look at this dedifferencing operator more and more detail. So if x is of type t star, which means in star, then the box and circle diagram is as follows. So this is x is of a so now x is pointer. Now x is a pointer in star x, right? So if you declare x, you have to have a box and circle diagram, and the value of x is in this circle. So when xv is the address of a location that contains a value v of type t, so what is xv? xv is another address. So let's say xv is another address. It's the address of a location that contains a value v of type t. So replace t by integer. That will make it easier. So now x is an in star pointer, right? In star x. So if in star x, the moment you have declared x, no matter whether it's a pointer or a local variable, you will have a box and circle associated with that x, right? So just the declaration makes it have a box and circle. So you have x and then you have a value inside x. Now we are saying that int or x is an integer pointer in star. So that value inside x, inside the box of x, that will be an address. That is not really a value. It is an address. It is an address to a location. And in that location, the value inside that location is of integer type. It has to be of integer type. If some integer is there inside that location. So how to represent? So just the declaration makes it have a box and circle, no matter whether it's a local or pointer. Then if it is a pointer, if x is a pointer, you will have another location. You will have another location associated with x. So now there are two locations. If x is a pointer. If x is a pointer, there are two locations. First location is there because you have declared x. Even if it was a local variable, just a single variable, you would have had that box and circle. Just because you declared it. Second, if x is a pointer, it has another location associated with it. That is another box and circle. Now, how do we know that what is the relationship between x and this other location? Inside x, which means inside the value in the location associated with x is actually an address. It is the address of that other box. And in that other box, there is a value. So xv is the address of that box. And in that box, there is a value which is of integer type. And what is that value? That value is actually x star or star x. So star x means it is the value in the location associated with the value xv. So it is a value, so this becomes very confusing. It is a value in the location associated with the value in the location associated with x. You understand this? What is star x? Star x is the value in the location associated with the value in the location associated with x. So 2 times. So what you basically do? You take x, x is a pointer, but since you have declared x, you have box and circle for x. You take that value inside that box and circle. That value is not a number. It is an address. So you take that value, you go to that address corresponding to that value. Then inside that address, there is another value. That value has to be an integer. If x is an integer pointer, that value becomes star x. So basically, star x points to this location, xv, and if you do star x, then the value that you get is that value inside xv. Do you understand this? Does the pointer picture clear out a little bit? Whenever you have pointer. Now, whenever you have a pointer and you don't initialize it, it throws an error, right? When you compile, it says point star x is not initialized. So what do you do to initialize it? If you want to write something in star x, what do you want to do? If you want to have some value in x, and you want to make star x equals 5, so you have int star x, and then in the next line you do star x equals 5. What happens? Will it compile? You have to do malloc. Right? If you don't do malloc, it will throw an error, compilation error. If not, it will do a segmentation fault. Right? So what is happening here? Why is it throwing segmentation fault? You did not do malloc. What happens when you do malloc? Yes, memory allocation to what? To that second box. Right? So it has associated with each pointer, there has to be 2 boxes. When you declare it in star x, you have just 1 box. That is the first box. You have to have a second box. How do you get a second box? By using malloc. So whenever you don't use malloc, might not throw a problem. It might not show a problem in compile time, but it will show a problem in execution. You will have segmentation fault. So next time you get segmentation fault in any of your projects or assignments, think hard whether you have that second box or not. Right? Most probably it is because you did not have that second box. That's why it's doing segmentation fault. So that's why whenever you want to have some value in star x, there are 3 steps to it. First, declare x in star x, then you do malloc and get that second box, and then you can do assignments. Right? So have this picture in mind. So now this v has to be an integer type value. And %x is what? %x is the address of that initial box. You have a question?
What happens when we say star x equals null?
Equals null.
No.
So what happens? Tell me. Star x equals null. He says what happens when we do star x equals null? What will happen? What is the meaning of that? First of all, you have to define the English meaning of that assignment. We know that star x equals some value means what? Take that value, put into the location associated with star x. That is the definition of our assignment. So what is the location associated with star x? It's the xv, right? And where do you put in the value? You put it inside this circle. So when you do star x equals null, this becomes null. Understand? What happens when you make x equals null? Pardon? Xv becomes null. If xv becomes null, there is no address. You cannot do star x. The moment you do star x, it will say error, segmentation fault. Because you made the entire xv equals null, so there is no address now associated with the pointer. So this is the entire picture. For int star x, this is the entire picture. Which means what is x? X is this variable which has a location associated with it. The location is %x. Now inside %x there is a value xv. That xv is basically an address. That address is to some memory address which you have allocated using malloc, right? when you do star x, what happens? Star x gives you the value v, which is in the location xv. That is the entire picture of a pointer. Now we can do weird things with pointers. We can have different types of associations. So we know L value and R value. So is star x an L value? Star x is an L value, right? Why? Because it is associated with this address xb. It's a location associated with this address. So star x is an L value. It's the location associated with star x, which is the location whose address is the value of the location associated with x. So that is what I was telling you. It becomes very confusing when you speak it or say it in English, right? Because it's extremely confusing when you say it in English. But when you look at the box and circle diagram, everything is simple. So when you do star x equals 100, what changes? Does that value v, right? The moment you do star x equals 100, so this will become 100. This value v. So which means that you copy the value 100 into the location associated with star x. Take 100, put it there. That is what it is. And the animation now messed up. Let's do one thing. Let's do it on the board. So now let's try to do an example and see what happens. So we have this following piece of code that int x, so we have declared two variables, int x and int z, right? We have declared two variables and we say that z equals integer, so we cast it to integer, and %x. Value at and %x equals 10, right? We do this and we say x equals, so we have these lines of code. Now can we draw the box and circle diagram for this? Can you take 2 minutes to draw the box and circle diagram? Okay, did we get it? So let's start discussing. So int x means what? You have to have a box and circle for x. Right. So let's do the box and circle for x. Whatever value we don't know yet, but we know that ampersand x is this one, this address, right? And let's say this is y. Let's say ampersand x is y. Let's have that notation. Then we have z. With respect to z also, we have, since we have declared it, we have a box and circle, right? Now what does this line of code do? This line of code says, okay, take ampersand x, which means that the address. Consider it that this is just an integer, right? So cast it as an integer. So consider it as an integer. So what happens here? This value y goes here. Now, there is an important distinction. Can I draw an arrow from this circle to this box? Why not? It's not a pointer because it's just a value. By just casting it, I made it a value. So now y is not an address. So y is not an address and z was not a pointer. So if I just made z equals ampersand x, it's not semantically correct. Because it's now the ampersand x is an address. Right? So that's why I cast it to an integer, put it into z. Z is not pointing to ampersand x. Z has just a value y. Then we did star ampersand x equals 10. What does this do? What will happen now? What is ampersand x? Ampersand is that address. So star of ampersand x means what? The value inside that location ampersand x. So 10 goes here, right? 10 becomes here. Now we have this statement x equals star of ampersand x. What is ampersand x? This address. What is star of ampersand x? The value of 10, right? So we take the 10 and put it at the same place. So nothing changes. So this is the box and circle diagram after this point, after we have executed this line. Do you understand? Is this understandable? Is this correct? Everybody understands this, right? Let's take another example, and this time a more complex example. All these are in the slides, but I have messed up the animation, so we are doing it on the board. Yeah.
When you had the value of y being in the value for z, would we made never mind. I figured out my answer.
Oh. Now we have this. Let's say int. So this is pointer to a pointer. So we have x, which is a pointer to a pointer, y, which is a pointer, integer z is a local variable. Now we are having fun. So x is we have to do malloc. So x is a pointer to a pointer. So you do pointer to a pointer, malloc, size of int star. Then you give y malloc, so int star malloc size of int, right? And then you do the following. So x equals we have ampersand y. We have y equals, yes, y equals ampersand z, and y equals star x. Yes, that is the code. So this is our code. Now we start representing all these variables in box and circle one by one by executing one line of code. Right. So now what happens when you have int star star x? After that declaration, what will happen?
A pointer to another box.
So how will the box and circle diagram look like? Just the first line of code. Starts are looking the same because we are just declaring, right? So for x, the moment you declare x, regardless of whether it's a local variable, whether it's a pointer, whether it's a pointer to a pointer, pointer to a pointer to a pointer, does not matter. The moment you declare x, you have this x, the name associated with the location, and it has some value. Right? It does not matter what it is. Then you declare int star y. Same thing. This declaration, so you have y, name associated with the location, and some value. The moment I have this, I can say that this is ampersand x, this is ampersand y. Then we have z. This is ampersand z. Now things get a little bit tricky. Right? Now what we are doing is you are saying that okay, I do a malloc. So the moment you do a malloc, what happens? What happens is you have some other location. The moment you do malloc, you have some location. You don't know what that location is. And in that location there is a value. And let's say that location is A. The address of that location is A. Let's assume somewhere A. Right? So if you have that location and you try to execute this line of code, what will happen? What should happen?
There should be a pointer from the value of the new box into the value of the old box.
So if you do this assignment, what does this assignment semantics say? It says that you have a new location, take the address of that location, put it into the value of x. Right? So which means that this becomes A. This becomes A, and then what happens? So if that becomes A, what is this arrow? How will you? Yes. So what is this arrow means? How will you access this arrow in code? Star x, right? So this becomes star x. Star x is now a location. Star x is an L value, we know. It can be an L value, right? So star x becomes that A. So that is the thing, that is what happens when you execute this line of code. So whenever you do malloc, what you do is you create a location and you take the address of that location, put it into the value of whatever you are doing malloc for. So once you do that, then what happens is that this value points to this address. So star of that name becomes this address. Do you understand? Everybody understands what happened when we executed this line of code, right? Anybody has any doubts? Yes.
What do you mean two star?
Yes.
Int star star X.
Yes, there are two stars. Int star star.
You mean pointer point to a pointer?
Yes, pointer pointing to a pointer.
Okay.
But this line of code, int star star, this line of code does not matter whether it's 2 pointers, 3 level pointers, 4 level pointers, does not matter. What does malloc do? Malloc creates a location A, let's say A is the address of that location, takes that address, puts it into the value of whatever name you gave here. Right? Now next what do? We say. So we do y equals int star malloc size of int. How will it look like now?
Create a new location.
Create a new location. So create a new location. Name it B. How will it look like?
The value of B is in Y.
The value of B, no, not the value of B. The B itself is in the value of Y. Right? If B itself is in the value of Y, how will you access this arrow? Star Y. Okay. So that is it's the same thing that happened with X. Same thing happened with Y. So at this point, we don't make any distinction between int star star and int star. It's the same thing that happened, right? Now we do X equals ampersand Y. Yes.
Since y has a value of b inside the circle,
Yes.
wouldn't it be just by using y how you can access the address b? Because wouldn't star y access the circle inside b?
Yes, it will access the circle inside B.
Because you pointed the box
Yes, so that's how we point. And that's how we represent.
by star y.
Yes. So star Y represents to that location, right? The arrow is to the location, but when you do star Y, it means the value inside this location. Right? But by drawing the star, we are not drawing it into that circle. We are drawing it up to that location. That's the convention that we are using.
So the reason we use a certain type to be star, not double star.
Pardon?
The reason why we can't just know the size of just a number, or we have to specifically say it's a single or a double, is because of the arrows.
No. It's your choice.
So you could have said in star, malloc size in star for a double or a single.
No, for a double point. So if it's a double pointer, we'll come to this a little bit later, but let me explain. So if it's a double pointer, you cannot really set size of int. I mean, you can set size of int, but then it won't hold a pointer. It will only hold a value.
What's the size of the double point versus the single?
Size of a double pointer is the size of a int star. Right? So int star size means what? It's a 32-bit integer, which is an address. Right? But what is the size of an int? Int is also 32-bit. But you could have also said that this int is an 8-bit. So here you can write size of int 8. Here you cannot write size of int 8. It has to be 32-bit. So you can potentially write size of int also.
So you can always replace in double star with 32.
With what? Yes, with the number 32 that you can.
So for star, you could replace in star with the size of what, 32?
If it's a 32-bit computer. If it's a 64-bit computer, you have to use a 64.
Do you still then need to set the type to use double star or star?
Yes.
Or you still need
Otherwise, there will be type mismatch, which will come to later. Right. So here, this size of it's a convenience. Size of int star gives you 32 or 64 based on whatever machine you have. You could replace the size of int star and write 32 or 64 also. That's fine. You could hard code it as well. But if you use size of, then it gives you automatically that instar is 32-bit based on different systems. So if you go from a 32-bit to 64-bit system, size of instar will give you 64 automatically. You don't have to worry about it. Otherwise, if you hard code it, you have to then change. You have to go and change.
If you said 64 always,
Pardon me?
you always just said 64.
Then it will waste space. If you go to a 32-bit system, you are using 64-bit to represent 32-bit addresses. So then all the top MSB 64, MSB 32 bits are all 0. Yeah, it will still work. But you keep more space for when you don't need it. Any other questions? Okay. So that is how you represent. So at this point we are not making any distinction between star star or in star. Then the next thing is, so only distinction is that the size, how much memory you keep, right? That is the only distinction. How much memory? What can you store inside that value? So if it's say if I had it int 8 here, then this value can only store 8 bits, and this value can store 32 bits. Right? So that is the distinction that we are making here. That is the only distinction that we are making. That what is the size of the value that these addresses can store. But we are not really representing it in that circle. So representation wise there is no difference if we use box and circle representation. Right? Now we do x equals ampersand y. What happens? What happens when we do x equals ampersand y?
The value of x is the address of y.
So where do we put the address of y?
In the circle of x.
It's a circle of x. So which means we remove a, we delete a, we replace a by ampersand y. So we have to redraw this one. So I have to take a picture. No, let's not remove it. Let's use a different color. So we remove x, a, we delete a, and instead we have ampersand here. So here we have ampersand y. Right? So if we have ampersand y, how will it look like? Will we have that arrow? We won't have that arrow. If we don't have that arrow, then what is star x? Will point to y, right? So which means star x will now become this. Now what is star x? Star x becomes b, right? Star x is b. What is b? Is b a value or an address?
Address.
B is an address. So this star y is the same thing as star x. Do you understand this? So if we do star x, then that means what? Star x is b, and star b means what? Is the value here, right? So star x is this arrow. So star y becomes same as star x if we execute this. Yes.
Is there a memory width in the location A?
Pardon?
Is there a memory width in the location A?
That will come to a little bit later. Yes, it is. You can never access A again. A is gone. Yes.
Can you go over that line of code again real quick? What you just did to
X equals ampersand y, right? Okay, so if x equals ampersand y, what is the assignment semantics? What does it say? It says that whatever is the value in this location associated with ampersand y, right? You take that and put it into x, the location associated with x. So what is it? This ampersand y, that value goes inside x, right? It goes inside x. So that means you remove a and replace it with ampersand y. So if you do that, if you remove a and replace it with ampersand y, then star x should point to this, right? If star x points to this, then star x is b. B is again pointing to another location. So that means star x is b and star b is this value. So this value is basically star x. So this arrow, this line, you can also, first of all, you can write it as star y. You can also write it as star x.
So does that eliminate the other pointer that has star x going to what we did now?
Yes.
Okay.
It just eliminates it. And as he said that this is memory wastage. You can never access A again. So there are these concepts of dangling pointers and dereference pointers. No, yes, so we'll come to that. Yes.
So the value inside of y is now a pointer. The value of y is a pointer.
Value inside Y.
Is that address?
B, right? Yes. It's an address.
An address.
Yes.
So if you wanted the value of y, you get the address.
Pardon?
Get that. Yeah.
Didn't understand.
If you wanted the value of y, you get the address.
Yes. Now star y points here as well as star x. Now let's do the second one. Y equals ampersand z. Which means what? Y equals ampersand z means what? What do you do if y is equal to ampersand z? Yes, so where do we put ampersand z? Okay. So we delete b and put ampersand z here. So now this is star y, which is also equals to star x. So yes, we delete that arrow. Do you understand?
We have nothing, right?
Pardon?
We have nothing, right?
Yes, z has nothing. Now we execute next line of code, which says y equals star x. Y equals star x. What is star x? Star x is this ampersand z, right? So do we change anything? Nothing changes. So now star y is what? Whatever is value in z. Now it's nothing, but we can put something. Z equals 5. Then what is star x? Star x points to y. Star x is this value inside z. And what happens to these two? Gone. You can't even free. You can't even free this malloc, right? So what happens here? These memory becomes garbage. It's just not used. It's just so that is basically bad code. You wrote very poor code. So we'll stop here and we'll continue from here.
So
Yeah, but files like.
yeah, I can go ahead and get it.